I'd like to invite you today to this webinar session. We will be talking about Steca's portfolio of PV off-grid inverters. So I'll get started right now so we don't lose any more time. This is the setup of a typical inverter system. We have, as A here, our PV modules. We have our solar charge controller, our PV charge controller, which is controlling the charge of the PV modules. We can optionally have some DC loads as well. This is typically a good idea if you're using, if you have a house, for example, or a cottage where you can maybe put your lighting and your refrigeration on a DC line on a separate circuit, because like this, you can have all the loads which are running many hours per day. So, for example, like lighting or refrigeration, cooling, you could have those running on a DC circuit. And then you can use your other loads, which you might only be using periodically. So, for example, in your kitchen, maybe your television, etc. You could use those on an inverter on a separate AC circuit. And you'll see later this basically helps reduce the total consumption because your inverter always has a certain amount of self-consumption. So in this case, in the typical design, we have a DC load as well, so this is optional, of course. Then we have the inverter, which is D. You'll notice here the inverter is directly connected to the battery. It is not connected to the DC output of the charge controller. And then finally, on the AC side, this is separate, so of course the left-hand side is the DC circuit, and on the right-hand side we have the AC circuit. So on the right-hand side, we have a galvanic isolation. We have our AC loads. So this is our typical setup. So here are 5 general rules you should keep in mind when you're designing systems with inverters inside. The first point is careful and conservative system sizing. We don't have the time today to go into detailed sizing of a PV off-grid system, but suffice to say that if you develop a PV off-grid system, and if you miscalculate only by a little bit the consumption, or rather the production compared to the consumption, then things can go wrong quite dramatically. So just to give you an example, for example, if you have a system which, let's say, consumes 1 kilowatt-hour per day, that is your consumption. So your PV modules, your batteries, also your charge controller, everything will be designed based upon this assumption that your customer is really consuming 1 kilowatt-hour per day. If by chance your customer is using 2 kilowatt-hours per day, then even if you've done your job correctly as a systems designer and installer, of course the PV consumption or the PV production will be too low for this much higher energy consumption than you initially expected. And what will happen is simply your battery will discharge over time. Even if the difference is very small, even if, for example, you're bringing 1 kilowatt-hour per day into the system, but you're extracting with your loads 1.001 kilowatt-hours. So even then you have a mismatch. You have less energy going in than is going out. So in this case, you will run into issues. So especially for inverters, because inverters are always quite inviting for customers to add additional loads, which maybe you didn't know about when you were designing the system. So here it's that much more important to have a careful and conservative system sizing. In other words, when in doubt, increase the PV array, increase the battery capacity to make sure that you can really serve those loads reliably. The second point is the battery capacity. This is a common question. What battery capacity should be chosen? Of course, the battery capacity, again, is something that you will find when you're sizing your system because it depends on things like your depth of discharge, on your autonomy, how many days your system can remain autonomous even if there's no recharging at all from PV or from any other energy source. But there is another consideration, which is there's always a minimum battery size for a given inverter. The reason is quite simple. You'll notice this from your car. If you have a very small battery in your car, or if your battery is very old, then you have difficulty starting your engine. your voltage simply drops very low because your battery is not capable of delivering the current that's required to start your engine. This is pretty much what happens when your battery is too small in an inverter system as well. An inverter obviously outputs a sine wave at about 50 hertz or maybe 60 hertz, depending on where you live. And in order to do so, it is taking energy on the DC side, so on the battery side, 100 times per second. So this is exactly twice the frequency that you have on the AC output. So the battery must be capable of delivering this impulse current. And that's why we need to have a certain minimum battery capacity to ensure that we have a reliable system even in the medium term. So our recommendation is to calculate your battery capacity in amp hours. You take 5 hours times the nominal inverter power. So if you have a 1 kilowatt inverter, then you take 1,000 watts. You divide that by your nominal battery voltage. So this is 12, 24, or 48 volts. And then you get your minimum battery capacity in amp hours. So your battery should have this capacity or larger at the voltage you've chosen. Now, there is obviously a lot of pressure from customers to reduce battery sizes because, of course, the battery is the most expensive component typically in any PV system, in any off-grid PV system at least. So customers will pressure you to reduce the battery size. In that case, with some of our inverters, for example, the SOLARIX PLI, we give you a certain value as an absolute minimum. So for the case of the SOLARIX PLI, regardless of whether it's the 5 kilowatt or the 2.4 kilowatt version, because they work with different battery voltages, the minimum battery capacity is always 200 amp hours. So this is significantly lower than our 5 times rule here. So this is our recommendation. And then the absolute minimum, for example, for the SOLARIX PLI is 200 amp hours at 24 volt for the smaller one, 48 volt for the larger one. But we'll see those models in a moment. Then use short and thick cables between the inverter and the battery. Typically, for off-grid inverters, very high currents are flowing between the battery and the inverter. And to ensure that we don't have too much voltage drop and that the system is running stably, we need to ensure that we have a certain minimum connection cable size, and that we also try to keep the distance between the inverter and the battery as small as possible and keep the cables as short as possible. With some of our inverters, the cables are already included. So for example, for the SOLARIX PI inverters, we already have 16 millimeter square cables that are prefabricated, so that are already attached to the inverter, so you don't need to worry too much about that. But for the bigger inverters where you design your own system, where you have to basically attach your own cables, make sure that you follow the instructions in terms of the cable cross-section. Otherwise, you'll run into issues. The fourth rule is to always connect the inverter directly to the battery. I'll switch back to the previous typical inverter system. As I mentioned before, the inverter is connected to the battery. It is not connected to the DC output of the charge controller. Now, the reason is this. Even if you think you have a sufficiently dimensioned charge controller, as in the output current of the charge controller should, in theory, be sufficient for your inverter, even under such circumstances, we strongly advise against connecting an inverter to the DC output. The reason is that we have these pulse currents, which I was just talking about, and so these are difficult to handle for the electronics, for the MOSFETs that are switching the load on and off, and also for our current measurement that we do on the DC output, which the values of those current measurements we use for some internal regulation, but also for the customer to show them how much energy is flowing out of the system. And we also use that for state of charge calculation. This current measurement is optimized for DC loads. So here we have 100 pulses basically per second that are going towards the inverter. So this current measurement is not able to keep up with that. So in other words, your current measurement will be off towards the inverter, and that will simply mean that your state of charge calculation will also be off. So in this case, if you don't have a charge controller with an external current sensor, you would need to switch the charge controller to voltage control mode, not to state of charge mode. And this is a requirement as soon as you connect something directly to the battery, which again is required for the inverters. They must be connected directly to the battery. As soon as you do that, you need to switch the charge controller to voltage control mode if it is capable of doing a state of charge calculation. So that's the fourth rule. The fifth one is we need one DC fuse for each inverter on the battery. Of course, you can use two fuses, one in the positive and the negative, but the minimum is one. It's important to use a fuse separately for each inverter for a couple of reasons. One reason is, of course, if you're using several inverters, and if you're using one fuse for all inverters and that fuse blows, well, then you've turned off your entire system, so you have absolutely no redundancy at all. And the second reason is that if you make the mistake of connecting the charge controller and the inverters on the same fuse, and that fuse blows, then what happens is the charge controller will not have a battery to regulate the voltage. So at least for a very short amount of time, usually the charge controller protects from this, but there can still be a small peak. The PV voltage will basically be visible on the battery connectors. And if the inverters are directly connected to those battery connectors via the same fuse connection, then the inverters could be damaged by the high PV voltage. So if we put a fuse separately on each charge controller and separately on each inverter, we don't have that issue. So this is our strong recommendation. Then the sixth point, the last point, is for the vast majority of applications, we recommend pure sine wave inverters. Steca sells nothing but pure sine wave inverters. We do not have any other forms of inverters. Other inverters can be cheaper, but of course the sine wave they emit isn't a sine wave. It's actually a square wave or a modified square wave or a modified sine wave, as some people call it. This can be used for light bulbs, incandescent light bulbs, or very, very, very simple loads. But for the vast majority of loads like laptops, like motors, etc., you would need to use pure sine wave inverters. So those are our 6 general sizing rules. Here you can see our main portfolio of inverters. On the small side, on the left, we start with the SOLARIX PI. They come in 450 watt and 900 watt units, and you can put up to 4 of them together on a single phase, so that we end up with a total system size of 450 watts to 3.6 kilowatts continuous power. All of the powers I'm giving you today are continuous power. Depending on the device, sometimes we have a higher 30-minute power rate, and for all of the devices, we have a certain overload capability, a peak capability for 5 seconds. So what I'm talking about here is the continuous power. So this is for pure single-phase loads. There's no connection at all to any grid, so this is really for a pure off-grid scenario. Then we have the SOLARIX PLI. Here we have 2 models, a 24-volt and a 48-volt variant. One is 2.4 kilowatts, the other one is 5 kilowatts, and you can put up to 9 of them together. So that means you can have up to 45 kilowatts, 5 kilowatts times 9. And here we have the choice to either hook them up in single phase or in 3-phase mode, if you use more than 1 unit. Of course, for a single unit, it's always single phase. So if you want to build a 3-phase system, you will need at least 3 inverters. And then finally, on the high-end scale and the highest power as well, we have the XTENDER series of inverters. They come in 3 different sizes. I'll introduce them to you later on. And here we start at 500 watts for the smallest model, and 7 kilowatts is the largest model, and we can put, again, 9 of them together to have up to 63 kilowatts. So we'll start off with the SOLARIX PI, which is the simplest form of inverter. As I've mentioned, these are all pure sine wave off-grid inverters. So that's a given at Steca. You will always have pure sine wave inverters. We have 4 specific models. The smallest one is the 12-volt, 450-watt model. Then we have a 450-watt, 24-volt model. Then we have a 900-watt, 24-volt model and a 900-watt, 48-volt model. Now, just to explain maybe the naming scheme of these inverters. So the SOLARIX PI is, of course, the name. Then we have a value here. So we have 500, 550, 1100, 1500. This value is the P30 power value. So it means that the unit can handle this size of load for 30 minutes. And then finally, the dash 12, dash 24, etc. should be obvious. That's the battery voltage, the nominal battery voltage. So for all of our inverters, that's our naming scheme. It's always the model, then we have the power for 30 minutes, and then we have the battery voltage. So depending on the model, they're different here. We have peak loads up to 2.8 kilowatts for 5 seconds. So this is specific to the SOLARIX PI 1500. For the other models, it's lower, so it's worth looking at the data sheet for that, depending on what kind of loads you're powering. Just for your information, if you're powering things like AC pumps or AC refrigerators, anything that has a motor, a compressor, something like that inside, you will need to deal with peaks at a very minimum of 2. So if you have, let's say, a 500-watt motor, you will have to deal with at least 1 kilowatt while it's starting up. But that's a very, very small number. To be honest, the vast majority use 5 to 10 times their nominal power at the peak. So this is something you really need to keep in mind. So if you have a 500-watt motor, chances are that while it's starting up, especially if it's older or if it's being blocked, so if the maximum current is flowing but the motor cannot turn freely, in that case you can deal with easily with currents to up to 10 times. So for 500-watt motors, you would need to deal with 5 kilowatts for probably just a few milliseconds, maybe a few tenths of a second, but just make sure that the inverter that you've chosen can deal with that. So the SOLARIX PI range is extensible with up to 4 units. In order to do so, you will need the PA Link 1. I'll show you a picture of that later. And you can use this as single-phase systems. Again, this cannot be used in a 3-phase system. We have a dynamic low-voltage battery protection. So there's a limit for when the unit turns off. I believe it's 10.5 or 11 volts as the absolute minimum. And then depending on how much load is applied, this is varied. So of course, if you have a big load on your inverter, then the battery voltage will be lower than even if you have exactly the same state of charge than if you have a small load, simply because of the internal resistance of the battery. So this device will dynamically compensate for that by changing the shutoff value for the low voltage disconnection. Then we have an easy control with a turning switch. You can see it on the front here. It looks a little bit like a thermostat. I'll explain the function of that later. We have an info LED right here, which gives you a running state. As I've mentioned, we've included the battery cables. They're directly connected to the unit. They are 16 millimeter square cables. And then finally, we have a very low consumption when the device is running with no loads. Specifically, I believe it's 6 watts for the 12-volt models and 10 watts for the larger models. And we also have an optional standby mode where we reduce that even further to about 0.5 to 0.6 watts. So these are definitely the most efficient inverters in terms of standby consumption or no load consumption. So let's look at the SOLARIX PI extensibility. Here we have an example of a fully extended system with 4 SOLARIX PI inverters. And you can see here we have the connection box, the PA Link 1. So as soon as you're using more than 1 inverter, you will require this box. If you're using a single inverter, you do not require this box. So you can use a single inverter by itself without this box. So because we can connect up to 4 PI inverters on this PA Link 1, it means for 30 minutes, we have a higher power, and of course, we have a peak load that's even higher than that. Then we have a very high redundancy. Because we're using 4 devices here, it means that if one slave fails, for example, well, then nothing at all will happen. You will simply lose a quarter of the maximum power. And even if the master fails, which is basically controlling all the others, then basically you only need to switch out the communication cable and the AC cable on the PA Link 1. and then you can go ahead and fix the master or whatever, if it's a warranty case, depending. But like this, if you're on a critical site, you can continue to run it by simply taking one of the slaves and replacing the master with it. So the units are always identical. It's just a question of where you connect them on the PA link 1. This should be obvious, but just to make sure you know, always use only the same model and size of PI inverters together. They should all be identical models. All of the 1 to 3 slaves, so you can use 2 inverters, 3 or 4 inverters. So each one of the slaves must have the turning switches set to the off position. I'd just quickly like to explain why. Let's say that there is somebody goes along and takes out these communication cables. These cables are very important because these cables handle the communication between the inverters for the synchronization. Of course, we have each inverter which is outputting a sine wave, and we need to make sure that these sine waves are synchronized, that they're all doing the same thing. If they're not, then we have a collision, and then we have potentially very high voltages colliding, and we will have damage of some sort. The same thing would happen if you would try to connect an off-grid inverter, which is not designed for it, to a grid. Then in that case, well, the grid will always win. It will simply destroy your inverter and possibly cause serious damage. So that's the reason why we expect the slave switches all to be turned off. Because like this, if you lose communication, the device will simply stop running. If you have the switch turned to on or any other position apart from off, then if you take out the communication, the device will continue to run. And then, of course, you have a very real risk that there's a collision of the AC sine waves. Now, I had one question asked, so I'll just check that question for a moment. The question asked was whether the inverters can supply load directly from PV without existing batteries. No, they cannot. None of our off-grid inverters are to be connected only to PV and without a battery. They're all battery inverters. So let's look at the possible positions for this turning switch. So I've already mentioned that for the slave, all of the switches must be turned to the off position for safety reasons. Now, what about the master? The good thing about the system is that we only need to worry about one turning switch. All of the other ones should always stay off. The master is the only one that we need to control. So we have 4 positions here. We have an off position on the very left. We have an on position on the right. And on the bottom right, we have all on. So these 3 conditions, I think, are quite simple to explain. Off means all of the inverters are off. So you have virtually no self-consumption. So if you're using a weekend house, for example, the customer can simply turn the switch from the master to off and be sure that all of the inverters in parallel are all off. Then there's the on position. So that's what we have here on the right in the middle. And this means that the master is always running. So that means that we always have 230 volts or 115 volts. These devices are also available in 115 volt versions. We can go ahead and be sure that we basically always have our own microgrid running at all times. The nice thing is that the master is controlling the slave. So let's say that you're using more power than the master can deliver. The master will simply dynamically and automatically connect the slaves depending on how much energy you need. So you don't have to worry about that. The slaves are basically always in standby, and they are controlled automatically by the master. But if you have the master set to on, you can be sure that in some form there's always a clean, pure sine wave in your system. Then there's another one which is all on, so you can probably guess. This means that all of the inverters are always running. So honestly, I don't think I've ever had a customer which has needed that setting. If for some reason you have very extreme peaks, it could theoretically happen that the system is not capable of powering or of activating the slaves in time. To be honest, very unlikely, because I think it takes about 1/2 wave to activate them, because it always happens at the passage through 0. But if for some reason you do have issues, so for example, maybe if you have an industrial estate, you have large machines, that kind of thing, you could also have them all running all the time. Of course, the downside of having all the inverters running all the time is that you will have the no load consumption of all the inverters as well. So if each converter is taking 6 watts, for example, then you have 24 watts of consumption because all 4 are running all the time. The nice thing about the on switch, where only the master is running, is you only have 6 watts consumption here, and then 0.5 to 0.6 watts for the others. So let's say another 1.5 watts roughly, so 7.5. So that's of course much lower, and especially for smaller systems, that can really reduce the amount of batteries and PV that you require. Then the final setting is the standby range. So all of this middle range is basically a range from about 2 to 50 watts that you can control, and this is related to the standby function of the inverter. So basically, if you have a house where you need to save as much energy as you can, so you don't want to leave the inverter running all the time, you can set this standby switch so that as soon as you power on your smallest load, the inverter automatically starts up. So what really happens is the inverter is sending out a sine wave once every second, just one wave or 1 or 2 wave packages, and it's checking if there is an AC load connected somewhere on the system. If there is an AC load connected, and if the AC load is consuming more than this threshold that you can control with a switch, then the inverter automatically starts up and does its job. So this is another way to reduce the consumption, the self-consumption, even further. So next we have the SOLARIX PLI family of inverters. Here we have 2 inverters. This is the smaller one, the 2400 minus 24. Again, this is the power. In this case, it's the same as the nominal power, but this is always the P30, so the 30-minute power, and this 24 means that's the nominal battery voltage. So here we can have 2.4 kilowatts at a 24-volt battery system. So here we have an inverter which can do much more than just convert DC to AC, which is what the SOLARIX PI could do. Because here we've also added a connection to an AC source. So this could be a grid or a generator. And on top of that, we also have an integrated MPPT charge controller. So we can connect the PV module directly to this inverter as well. So we have 2.4 kilowatts of continuous power and 3.0 kVA. So if you have any power factor which is below 1, you can get even more out of it. And for 5 seconds, you can provide twice that, so 2.8 kilowatts. Then we have a 40 amp MPPT charge controller with a maximum PV voltage of 100 volts. So typically this will mean that you will use, if you're using 60 cell PV modules, which I think are the most abundant on the market and also the cheapest, you use two of them in series, and then you connect several of those strings in parallel. Then we have a 60 amp charger from an AC source. So again, this could be either the grid or a generator, regardless. Of course, through programming of the unit, you can define priorities, such as when the grid should be used, when PV should be used, whether you want to prioritize one over the other, depending on your battery voltage, all those kinds of things. So all of this programming is done via the buttons directly in the menu of the device. So basically, the only thing you need here is fuses and surge protectors. That's the only additional thing you need, apart from the battery and the PV modules, of course. And obviously, we, for safety reasons, we also recommend an RCD, which I'll explain in a moment. You can use this either purely off-grid, so you don't need to connect anything to the AC input. You can use it in a pure off-grid system with no AC source at all, apart from the inverter itself. Or you can use it in an on-grid scenario or with a generator, and you can be sure that there will never be any injection into the grid. It is physically impossible for this device to inject into the grid, even for just a few milliseconds. It cannot do that. We also have an automatic generator start. So we have a relay contact on the inverter on the bottom, so you can give a signal when the battery voltage is low to start a generator. Then, as I said, the priority is selectable between solar or AC source. We are always synchronized to the grid, so as soon as there's a valid signal on the AC input connector, so as soon as there's a valid sine wave, basically, the inverter will automatically synchronize to that sine wave, so that if it needs to switch over, then it's already synchronized beforehand, so we can switch over very, very quickly in 10 milliseconds. So that's basically 1/2 wave. Honestly, so far, we've from the SOLARIX PLI, we've sold a couple thousand, and we haven't had a single case where a customer said that the loads were not capable of handling the switch over time. So even very sensitive loads are able to deal with 1/2 wave of loss during switching. Then there's an overload bypass function as well. So if, for example, you're using more than 2.4 kilowatt, then the inverter can automatically switch over to the AC source, for example, the grid, so that you can even take up to 5 kilowatts or 6 or 7 even from the grid. And as soon as it's finished, of course, there's a certain timeout, so you don't switch back and forth too often. As soon as it's finished, it then switches back to off-grid mode if that's your priority. And finally, it's very light at 7.6 kilograms. Then we have the big brother, which has exactly the same functionality, so I think I don't need to explain it all again. The differences are, of course, the values, the power ratings. We have a 5 kilowatt inverter in this version. It's a 48 volt model for 48 volt batteries. And we can deliver 10 kilowatts for up to 5 seconds. Here we have an 80 amp MPPT charge controller with a maximum DC voltage or PV voltage of 145 volts. So in practice, this means 3 modules instead of 2 of the 60 cell crystalline modules in series, and then we build several strings in parallel. We also have a 60 amp charger, again from an AC source, so grid or generator. All the rest is pretty much the same, except for the weight. Of course, it's a little bit heavier because it has twice the power. It weighs 11.5 kilograms. So here's an example of a pure off-grid system. So here we have absolutely no AC source. We, as the only energy source, we have PV. Then we have our electrical loads with our AC loads with 230 volts and the battery connection. So you see here, there's absolutely nothing connected to the AC input. Then we have the opposite example. Here we are using no PV. So we can go ahead and use this as an uninterruptible power supply, a UPS as well. We simply connect nothing to the PV connector, and the inverter can then charge from the grid. And as soon as the grid fails, it will switch over within 10 milliseconds and provide the power from the battery. And then we can mix the two, of course, which is, I think, the most typical scenario, where, again, we have the AC loads on the AC output. We have PV modules this time on the PV input. Of course, we have a battery. As I mentioned before, all of our inverters require a battery. And then finally, we have a diesel generator or a public grid on the AC input side. If you're using both a public grid and a diesel generator, you will need to have an external switch. It can be an automatic switch, but it must be externally controlled. The PLI cannot control it. The PLI can only deal with one AC input. But if you have a priority selector outside of the SOLARIX PLI, you can deal with two AC inputs by simply choosing one or the other at any point in time. Also, you don't need to worry too much about the switchover time here, because as soon as the inverter detects a loss during your switching, it will automatically switch over to the battery. And then once you have a stable AC voltage again on the AC input, it can then switch to that new source after, of course, it has synchronized to that source. So this, basically, the PLI takes away all the heavy lifting of switching quickly and of synchronization. You don't need to worry about that. So this is to give you an impression of what the connection area looks like on the SOLARIX PLI. We have the AC input on the left-hand side. So this is PE, the grounding, the live wire and the neutral wire. And then we have the same for the AC output. So this is where you connect your loads on the AC output. We have an AC input breaker, because of course we can switch over to the AC source. And in that case, we still need to have some kind of protection if you're overloading the input source. So in this case, we have a 30 amp input breaker. So that's the maximum current that you can provide basically from the AC source to the load. It's 30 amps. Then we have a serial RS-232 connection for data. You can, if you need the protocol, you can request it at Steca. We will send that out to you. Also for USB, also for data. Then we have the dry contact, the relay contact, which is typically used to start generators, for example, or to signal when you require power, basically. Then we have the inverter on-off switch. Now, this switch is only the inverter portion. So basically, let's go back to our example of a weekend home. Or any site where you only need the inverter basically periodically while you're there, you can go ahead and simply switch the inverter off with a switch, but the charge controller will still continue to run. And so basically the switch is only switching on and off the inverter. The actual PV charging will continue to run regardless of the setting. What will happen is basically during the night, the inverter will be completely off, the display will be off, everything will be off to conserve energy. And during the day, as soon as you have enough PV voltage on the PV input, which is here, the inverter will automatically, or basically the device will automatically start up, start the display, start the charge controller, but the actual inverter portion will remain off. And then finally, we have the battery connection here. The ring terminals are already included in the package of the SOLARIX PLI. So the recommended cable cross-section for this is 35 to 50 millimeters square. This is the 5 kilowatt, 48 volt version, very similar. Again, we have an AC input, AC output. The AC input breaker is slightly larger now. It's designed for 40 amps, which is equivalent to about 9.2 kilowatts for a 230 volt system. So that's how much energy you can take from the AC input. That's the absolute maximum that you can pass through the device. Just like for the smaller version, we have the RS-232 and USB communication terminals. We have, again, a relay contact to start a generator if required. So, of course, this is optional. Same story for the on-off switch. It's only relevant to the inverter itself, not to the charge controller. And again, battery connection, the ring terminals are included, and we have the PV input right here between the fans. So what if 5 kilowatts is not sufficient, or in a 24 volt system if 2.4 kilowatts is not sufficient? For the SOLARIX PLI, you can extend them. Basically, what you need is what we call a parallel kit. It's actually a parallel or three-phase kit because you can either use it for a single-phase system or for a three-phase system. You need one kit for each SOLARIX PLI that you intend to connect together. So you can use 2, 3, 4, up to 9 inverters together in a single synchronized system. So basically, this means that for the 5 kilowatt version, times 9 means the maximum system size is 45 kilowatts. So up to 9 can either be put on a single phase or distributed across 3 phases. Same goes for the smaller 2.4 kilowatt version, which means that our maximum synchronized system size is 21.6 kilowatts. There's one small note. I've mentioned before the switchover time from the grid or from the AC source to the off-grid mode is 10 milliseconds for a single device. If you're using more than one device, then this switchover time can be longer, particularly in a 3-phase system. The absolute maximum is 50 milliseconds as a switchover time, even if you're using 9 3-phase devices. So just keep that in mind that the switchover time will be slightly longer if you're using the system with several SOLARIX PLI inverters connected together. So in the parallel kit, you will receive the parallel board itself. There's 2 versions. They're slightly different for the 24 volt and the 48 volt inverters. And then, and this is the same between both versions, there's the communication cable and there's a current sharing cable. You'll see in a moment what the difference is between those 2. So here we have an example for a single phase parallel connection of 3 SOLARIX PLI inverters. They must all be connected to the same battery. This goes for anytime you interconnect multiple PLIs in a synchronized system, you always need to connect them all to the same battery. This is a requirement. Then we have a single AC source, and we simply connect all the inverters in parallel on the AC source. And then same thing goes for the load. The load outputs are all parallelized, and then like that, this is where your consumers are. So down here, we have a diagram of how to connect the communication and the parallel cables, the current sharing cables. Basically, the orange lines here are the communication cables. So here, this is where we synchronize parameters. This is where, if we have a three-phase system, we do the phase shifting of the phases, 120-degree phase shift. So all of the digital communication happens across those cables. But because we're using 3 inverters on a single phase, we need to make sure that the power that we require is distributed evenly across all the inverters. Because otherwise what would happen is one inverter would maybe be delivering 5 kilowatts and the other 2, 1 kilowatt. And that means that that single inverter will go into overload much more quickly than the others will. So it's important to keep all the inverters which are in parallel on one phase running at the same power level. So that's what the cables in green here do. Those are the current sharing cables. So every time you have more than one SOLARIX PLI on a single phase interconnected, you need to use these current sharing cables which are included in the parallel kit. So this was an example of a single phase system with 3 inverters, 3 SOLARIX PLI. Now we have exactly the same thing except in a 3-phase system. So again, we're connecting all the inverters on the same battery. This is again a requirement. We connect the neutral, obviously the same neutral for each inverter, and then we connect phase 1, 2, and 3 to the various inverters. And on the load output, we do the same. We distribute that as a 3-phase system. You'll see here, there's no green cables. We have the communication cables, which we always require, so that we can do our phase shift between the 3 devices, again, and for parameters, etc. But the difference is, we have nothing connected to the current sharing cables now. And the reason is that now we have only one single inverter per phase. So there's no need for the inverter to share the load on a single phase with another inverter. But again, as soon as you're using more than one inverter on a single phase, you need to use these current sharing cables on that phase. And then if you want to go even bigger, as I said, the maximum is 9 inverters in a single synchronized system. So that would be this in a 3-phase system. But you can also use asymmetrical phases. You can go ahead and put, in this case, 3 inverters on phase 1, 2 inverters on phase 2, and 1 on phase 3. You can even go ahead and use 7 inverters on phase 1 and 1 each on phase 2 and 3. So you're very flexible in how you distribute those inverters. So for example, if maybe you have a house, most of the house is running on a single phase, so you want to put 2 or 3 or more inverters on one phase, and then maybe you have just a few 3-phase loads, and in that case, you would need to maybe just 1 inverter for each of the other phases. Now to the AC grounding and operator protection. It's necessary to ground the SOLARIX PLI. By the way, it is not absolutely necessary to ground the SOLARIX PI. It is a protection class 2 device, so it's not absolutely necessary. But for protection of operators, you may be required to do so depending on your country to be able to run a residual current device. But for the functionality, it's not required. For the SOLARIX PLI, for safety reasons, we do need a ground connection. And what's interesting is if you've ever looked at residual current devices, you'll know that they only work if there's a working ground connection. So typically the ground connection is the PE is connected to the neutral. This typically happens either in your home or maybe already at the electricity provider. But at some point there's typically a bridge between the neutral and ground. And this bridge is before the AC input of your SOLARIX PLI. Now, if your SOLARIX PLI is working in off-grid mode, it disconnects both the live wire and the neutral wire from your AC source. And in this case, your neutral would be what's called floating. In other words, the connection between ground and neutral is no longer there. For this reason, as soon as the inverter switches over to off-grid mode, we automatically, with the same relay that is used to switch over, we automatically connect the neutral and ground lines together. And this is to ensure that if you're using a residual current device, an RCD, to protect people basically from high voltage on the AC output side, as you would in most homes, you don't need to worry about the bridging of the neutral and the ground, because this is typically already existent in your home. And for the off-grid mode, the inverter is basically taking that over for you. So this is what that will look like in practice. You will have your AC source. So let's take the grid as an example. You have your bridge between the neutral, which is blue here, and the ground, which is green here. So this is typically already installed in the home. That's what's connected to your AC input. On the AC output, we have our loads connected to the live wire and the neutral wire, potentially also connected to the ground depending on your load. Sometimes you need it, sometimes you don't. And here you have your residual current device. And here, basically the connection between neutral and ground is made as soon as the inverter is switching to off-grid mode automatically. So that was the SOLARIX PLI family of inverters. We have some more webinars where we go into more detail. So if you're interested, you can check our webinars and join a webinar specifically for the SOLARIX PLI. And maybe to mention some of the limitation of the SOLARIX PLI in order for you to better understand the difference between the SOLARIX PLI and the extenders. The SOLARIX PLI, they cannot mix energy from the AC input and energy from your battery or from your PV. They can only switch back and forth. They can do so very quickly, like I said, in 10 milliseconds, but they can never mix the two. This has advantages and disadvantages. The obvious advantage is it's absolutely impossible to inject any energy into the grid, or if you're using a generator, to backfeed into the generator. So that's definitely an advantage. The downside, of course, is that if you want to inject into the grid, you cannot with that device, with the SOLARIX PLI. And also, you cannot, for example, mix and say, I want to take 2 kilowatts from my inverter, 2 kilowatts from my generator, for example, and I want to add 1 kilowatt from the battery, because my generator, for example, can only handle 2 kilowatts. You cannot do that with the SOLARIX PLI. You can either power all of your loads with the inverter or none of your loads with the inverter. And of course, it can switch back automatically. Now, the extenders are different in that you can mix AC input and the power coming from the battery. This also means that in some countries, you need to look out for your energy provider. Basically, you need to prove that you're not injecting power into the grid, and these devices can inject power into the grid. Specifically for the XTM series, because it's the most popular series, the middle size one here, you see in the middle. Here we have the necessary certification for Germany, at least the ARN 4105 that you require to show your energy provider, because there is a possibility to inject into the grid. Of course, this is fully up to you. You can program the inverter not to inject into the grid, but some energy providers are more picky than others. So this is a case where you need to basically prove to them that you're not, or that if you're injecting, that you're injecting according to the law. So that's one difference. You can mix AC input and DC, or basically battery energy or PV energy. And the other thing is the AC output of the extender is bidirectional. This is not the case for the SOLARIX PLI. So for example, you would not be able to connect a grid inverter to the AC output of the SOLARIX PLI. That would potentially just cause an error. There's an error for that on the SOLARIX PLI, but possibly even damage the SOLARIX PLI. For the case of the extenders, they have a bidirectional AC output, and this means that you can operate them with a grid inverter in what's called an AC coupling system. I'll explain that in a moment. So let's focus on the devices themselves. They do not have a PV connection directly. So these are pure off-grid inverters. They can be used with the grid. They can be used also to inject into the grid. But for the PV side, if you're using PV, you definitely need to add a charge controller as well to the system. There's no integrated charge controller in the extenders. So for these three classes of devices, they have pretty much exactly the same functionality. The difference is mainly the sizes. The smallest one, the XTS, which has the added benefit of having a higher protection. So it's more or less waterproof at IP54. Comes in sizes from 500 watts to 900. That's a small mistake, 900 kilowatts. In fact, it's 900 watts. and with a peak power of 2.3 to 2.8 kilowatts for 5 seconds. So you can see here there's various different values depending on which model you choose. There's 12 volt, 24, and 48 volt models that we have, but they are separate. So you cannot switch from one to the next because, of course, the transformer on the inside is suited to your battery. So depending on which model you choose, you have different battery charging currents. That's just the maximum value. You can program that in the device itself. The XTM is pretty much the same thing. Here we have an IP20 housing, higher powers, and of course, higher charging powers as well. And then finally, the XTH, those are the largest ones. They go all the way up to 7 kilowatts and 21 kilowatts for 5 seconds. So it's pretty much always times 3, except for a few special cases on the XTS. All the other ones can handle 3 times the nominal power in overload. Then, as I just said, we can do AC coupling because we have a bidirectional AC output. Grid injection is possible. So we can inject, for example, when the battery is full, we can inject excess energy into the grid. We can use this with a generator. And also here we have relay contacts on the XTM and the XTH. For the XTS, there's a relay module which you can buy separately, so you can add that as well. We can use these contacts to control a generator, for example, but we can do much more as well. We can do much more than with a SOLARIX PLI. We can program the contact for certain time slots. We can program them to give you maybe an alarm status, all sorts of things. There are several hundred parameters we can program on the extenders, as opposed to the SOLARIX PLI, where we have about 35. And then finally, this is very similar to the SOLARIX PLI. We can synchronize to the grid and have fast UPS type switching. So again, 10 to 20 millisecond switching time. For all of the extenders, we have an optional accessory, which is the RCC02. There's a special version of the RCC02, which is called the RCC03, which has exactly the same functionality. The only difference is it's made for integration into a wall. And this is basically a device which you screw onto the wall. The other one is a device which you slide into a wall to make it flush with the wall. So this serves, first of all, as a display for multiple devices. If I go back, you'll see that on the front, we don't have a liquid crystal display. We just have basically a group of LEDs, which are good for debugging and giving you a very rough state of service for the device. But of course, it doesn't give you any exact values on how much power you're using, etc. So that's what the RCC02 is for. You can already sort of see it on the display. It shows you the current state. It shows you voltages, currents, powers, and temperature, all kinds of things. So you can use that as an advanced user interface. You can see all your current measurement values and parameters. Like I said, there's literally hundreds of parameters you can set on the extenders. In practice, you typically only need to set about 5 to 10 parameters, depending on your type of battery, mostly, and depending on your priorities, whether you want to prioritize the battery side or prioritize the AC input. That's up to you. Then there's also a remote input contact. So especially for the XTH, and this you can also add to the smaller XTS and XTM. You can also give a signal from the outside to the extender. So for example, you can have a switch which you wire to the remote input contact, and then you can program the extender to do something when you switch that switch. So for example, you can tell the extender to switch to the grid if you flip that switch and not worry about synchronization, all that, because the extender does that for you. Or you can tell it to stop charging, for example, if you flick a switch, that kind of thing. So you can also give an input into the extender while it's running. The RCC02 also has an SD card slot, which is the black part you see on the left here. When you insert an SD card, you can use it either for data logging. So once a minute, all of the data is logged. And alternatively, you can also use it to save your parameters or to upload or to download your parameters to the SD card. So if you're using, for example, a certain type of battery, you can set up all of your parameters, save them to SD card, go to the next device, then copy all the data across. You can also use this as a pure programming unit. So you can program the extender the way you like it, disconnect the RCC02, and send only the inverter to your customer, and like that, you're pretty sure that the customer cannot change any settings. But even if you send out the RCC02 with the extender, there's different user levels. So you can, for example, program the RCC02 to be in read-only mode, queue-only mode, and like that, you don't have to worry about your customers changing any of the values. And then there's various levels, intermediate levels. There's an expert level where you can change about 2/3 of the values, and then there's an installer level where you can change pretty much all of the values. So there's various access levels to that. I was just asked whether there's a Wi-Fi connection for the extenders. There's an external module called the the XCOM LAN, which is a connection to a local area network, and then you can use a portal to fully access your extenders remotely. For the SOLARIX PI, we don't have this year. We're expecting that around October to November, where we will have a Wi-Fi module which you can connect to the SOLARIX PLI, so that you can see all of the values on the portal. So as a very last subject, I started about 5 minutes late, so sorry about that. So we'll go till about 10:05, and then you can have a chance to ask any specific questions you might have. Let's look at AC coupling. So as I mentioned, the extenders have a bidirectional AC output. What this means is even if in a completely off-grid environment where you have absolutely no connection to the grid, you can use grid inverters. So what you do basically see here would be the extenders. They're connected to the battery. On the AC output, you have your loads, which is, I think, the normal setup, what we had initially during the session, where your AC loads are connected. But on the same, let's call it a microgrid that you've just created from your inverter, you can also connect grid inverters. And they will convert, obviously, the DC energy from your PV modules to AC, and they will both directly power your loads as a first priority, and as a second priority, if you have excess energy, that energy will be rectified by the extender and charged into your battery. So even though the extender doesn't have a direct PV connection, you can use the AC output to then connect grid inverters in an off-grid environment. Now there are 2 points that you need to keep in mind. The first one is what happens when the battery is empty, and the other one is what happens when the battery is full. Now let's look at what happens when the battery is full. The extender somehow needs to give a signal to your grid-connected inverters, or it could also be a grid-connected wind generator, for example, that is made for injection into the grid. You somehow need to signal to these energy sources that the battery is full, that you no longer require energy. So what you can do is the extender can simply switch the frequency. So we'll go, let's say, from 50 to 54 hertz or 52 hertz. You can set it however you like. And this will make absolutely no difference to your loads. They will continue to run normally. But your generators, your PV generator or your wind generator, they will notice that the frequency of what it thinks is the grid has switched to a higher level and that it needs to stop producing. So that's how you prevent your battery from being overcharged. Now you have 2 choices here. Either you simply switch between 2 values. So normal is, let's say, 50 hertz. And if you want to stop the energy flowing, you go to 52 hertz. Or you can also have a frequency ramp. So you can proportionally change the frequency depending on how much energy you still need. So this, of course, gives a much smoother regulation of current going towards your battery. Now, all of our grid inverters have what's called a droop mode. This is simply a country code which you select. So you can select Germany, Italy, or droop mode as a country code. And for the droop mode, what happens is exactly that. The Steca grid will react proportionally to the frequency that the extender is providing to it. So like that, let's say if you have 3 kilowatts currently being produced on your grid inverter, but the extender only needs 1.5 kilowatts, it will increase the frequency just enough so that it receives 1.5 kilowatts from the Steca grid. And now, as a very final point, we need to keep in mind what happens when the system has too little energy, so when there's not enough sunshine, when the battery voltage is running low. There's a few things you can do. Either you can connect the loads, the AC loads, via a large AC contactor to one of the auxiliary relays of the extender, which you can program freely. So you can, for example, tell the relay to switch off the loads at, let's say, 42 volts, for example. And then you still leave the AC grid running, the inverter running, so that PV can continue to charge the extender. Or you can have an external separate source of energy, so you can connect on the DC side, you connect a standard charge controller, MPPT or not, regardless, to connect directly from PV to the battery so that you can recharge the battery even if all of this AC side has shut down. Or the third option is you use a generator to inject into the battery. If you do use a generator, you need to make sure that you turn off the grid inverters while the generator is running. This is to avoid any possible backfeeding of the generator into the grid inverters. Under normal circumstances, backfeeding does not happen because the extender will simply rectify that energy and pump it into the battery. But just to be sure, we strongly recommend to switch off the grid inverters while the generator is running. So that's almost everything I have for you today, except for one very last example, just to show you some of the things you can do with the extenders. So this is just an example of a PV system. So we have PV modules here, which are connected to a charge controller, which in turn is connected to the battery. So this is similar to the drawing we had at the very beginning of the session. But now we've added some complexity to it. We've added the extender inverter on the battery directly. Remember, first of all, this doesn't have a DC output, but even if it did, the extender must be connected to the battery directly. And additionally, we have a generator as a second energy source. Now, this generator can either be controlled by the charge controller in this case, or you can also control it by the extender, regardless. Either one of the two can give the generator a signal to start running when the battery is low, for example. And then finally, we also have a current sensor in the system, which can measure up to 400 amps. Now, the reason we have the current sensor is so that we can see how much energy is flowing into the inverter or is flowing back, because obviously when the generator is running and we're charging the battery, there's energy flowing back into the battery. So this current sensor can sense that energy going either out or into the battery and reports that energy back to the charge controller. Now, the charge controller can use that, first of all, to show you how much energy is flowing in and out of your battery, to log that data either locally in internal memory or on an SD card, or it can also use that to calculate the state of charge of your battery. And again, to calculate the state of charge, we need to know the current going in and out of the battery. So we need to have an external current sensor if you're connecting an inverter to the battery. And then finally, I don't have that in this session, but this charge controller could also be connected to an internet portal. So then you would also need the current sensor to be able to see how much energy is flowing out to the inverter.